Okay, this is the video lecture for Algebra 2, Unit 5, Lesson 5.7. All right, this is going to talk about polynomial identities. All right, and what might identities be? Some examples of them are distributive, associative, additive, and commutative. All right, and you may not remember that these are these things called identities because we've been using them for so long. All right, but basically it's a set of rules that can shorten things, right, and help us solve math easily. All right, so we're going to talk about how polynomial expressions can have their own identities, what the patterns are, and how to really use those patterns then to solve for different factors. All right, so for polynomial identities here, okay, an identity is like an icon, right? Sure. It gives you a shortcut without wearing you wanting, oh my gosh, apologies. It gives you a shortcut for getting to what you want, right? A final end thing. So it shortens problem solving. Okay. Looking here, all right, so this is an example about counting grizzly bears. And this one's saying that they have to have a certain amount of food and figuring out how much they eat. All right, but it's saying we could either pull out a calculator or we could use an identity. All right, and so for this one here, it says find the total numbers of berries eaten by Tiny and Slim. All right, you could then just use, instead of using a calculator, you could notice that both numbers are close to a number that's easy to use, right? So 10,000, and they're a common element away from it. Okay, so what this is saying here is if we have both numbers similar to this thing called 1,000, we can use this as kind of a launching point. So looking at something simple here, right? We have A plus B. If we give it an identity here, you could say A plus B is equal to A plus C minus B minus C. All right? Where C is the common element. All right? C is the common element. All right? Giving it, sorry, the way that this is expressed here is gives a little extra to one and takes a little extra away from the other. All right, so we can use this principle to find out the number of berries. So using that mathematical identity above, again, 10,000 would be our common element. All right, so if 10,000 is our common element, we can say, all right, well, one of these plus 4 and one of these minus 4. So the common element for them is 4. Right? So we gave a little and we take a little. So we have 90, this value here plus 4 and this value here minus 4, which is like saying A plus B. All right, which is like saying A plus B. So then what we can do is we can add them together to find the sum, right? Add them together to find the sum, right? And again, basically what that is we took those 4 extra from 10,000 and added it there to the 9996 value, right? So this is just a step to simplify addition, all right? Just a step to simplify addition, all right? Now we kind of know what identities are, we can apply the same concept here to our polynomials. All right, now this is an identity that works for any value of x. Okay, it works for any value of x, where it's 2x plus x gives us 3x. Right, it kind of seems like a, well, duh. All right, but think about it, trust me, okay, it'll make more sense as we keep going here. All right, but basically what we could do with the left hand side is we could factor out an x value, right? And we could factor out, and that's 2 plus 1, right? So 2 plus 1, which gives us 3, which is the same thing as our right-hand side, which is our 3x, right? It's the same thing as our 3x. Okay, for the same reason, if I look at this value here, I've got 2x plus 5y plus y minus x equals x plus 6y. Again, question goes, what the heck? Okay, but you can use that as an identity, because what happens is if we factor out x plus y, from this entire quantity here, okay, we end up getting, and we add it together, right? If we have our 2x and our negative 1x, right, added together, that gives us 1x. Same as 5y plus 1y, right? 5 plus 1 gives us 6. All right. Now, doing this in graphical form could be a little bit more complicated here. All right. But we have our second degree polynomial, again, that U shape, and then our third degree polynomial, which is this S shape. So using a polynomial identity could be a simple way to express a polynomial in a form that is more useful. All right, and notifying here what they mean by polynomial expression, or sorry, polynomial identity. It is an expression that is set equal to a different representation or an equivalent form. All right, so by that it means, right, the left-hand side is equal to the right-hand side. So the left-hand side has to be equal to the right-hand side. So again, an example here is x minus y and x plus y. That's x squared minus y squared if we FOIL that out, right? And similarly here, ax minus y, and that quantity is squared, is like saying a squared times x squared minus 2ax plus y squared. Again, these should look kind of familiar here, right? And we've been using them, but now we're trying to put names to what we are doing. All right. So then here, when are identities useful? All right. They are useful, of course, if we can plug them into our real world life examples here. All right. But again, as always, it might not be as obvious that you're using or could use some of these things, right? So for example, here, we could use polynomials in backyard sports. So this is the one they gave you where t represents time. And then it says, this could actually describe the path of the flight of a football or a baseball. All right, so determining which identity is useful, right, is hopefully pretty simple here. Okay, we've got our t squared plus our 9t plus our 3. And what's funny about this one is okay, even if I take out some numbers, okay, it's not helpful to change this to a different identity. And that's what this is saying here. It tells you nothing new about the polynomial. So some of them are very trivial or very simple. So they don't help you at all. Okay. It considered trivial. Right. One of them here that's been really helpful for us is this difference of squares here. So if I have the expression, again, in a squared minus b squared, it gets simplified into this form here. All right. So again, starting with our a minus b squared, we add our 0 term for the identity property. And then we can substitute in a b plus ab, and then associative property, factor the common terms, right? And this is what we're left with. All right, so that's one of the ways that we could do that, right? It's a little bit different than what we've seen it, but this is the proof showing that this works. All right, and so again, knowing that this is the proof here, if we have an expression that's in this a squared minus b squared, right, we just go straight here. We don't even have to worry about doing the steps, right? And so that would be an example of using that identity. All right, so this is really, really helpful when we're finding complex factors, right? So looking at those different numbers, trying to do the complex ones, or rationalizing irrational denominators, right? So if we start with our given expression here, 5 over the square root of 7 plus 5, okay, we can change the sign of the second term in the denominator. Okay, change the sign of the second term, make that a minus. Then we multiply both of them, right? So we multiply by the complex conjugate, and then that's basically like saying 1 over 1. So when we multiply by the complex conjugate here, what we can do is we can then get the bottom, the denominator, into something more friendly for us to work with, right? So then we can simplify the bottom into minus 18, and then if we can do divisions, we would do them, but since this is as low as we can go. So this is another way of rationalizing things that are very, very complicated to simplify. All right, then this is a new one here potentially for us, difference of cubes. All right, difference of cubes, that's saying a cubed minus b cubed, right? And what this is going to result in, it's going to result in a minus b multiplied by our property that we've known before, our a squared plus ab plus b squared. All right, so what this is saying is our first expression is a third degree polynomial with 2 variables. All right, so this is a really a potentially useful identity, because again, instead of having to try to figure out how to find both of these, okay, we can just use this theorem here. So if we start with the given expression here, this is to identify that this works, right? If we expand into all possible terms, right, having those zeros, all right, it gives us this this expression here. We can then replace that expression and rearrange our terms. And again, when we simplify it down, it gets to our answer on the right-hand side. All right, so again, this is just proving that this works. Okay, you do not need to go through these entire steps here. All you need to know is that, okay, if I say or see a cubed minus b cubed, I can go right here based on this identity. All right, so then here, instead of the difference of cubes, we have the sum of cubes. We have the sum of cubes. All right, again, the subtle difference here being that this is now a minus sign instead of a positive sign, and this one is now a positive instead of a minus. All right, so skipping the steps here, again, it's the same thing there. All right, and then bringing it back to something that hopefully you've talked about before is this thing called Pythagorean theorem, right? Where c squared is equal to a squared plus b squared. All right, or a squared plus b squared equals c squared. All right, and this idea here uses squared terms to result in a new output. All right, so if we can look at how this applies to the same principles as our polynomials here, okay, again, look at the identity a plus b squared and a minus b squared. All right, if we substitute in x squared for a and y squared for b, we get out the following. Okay, we get out the following. And what these are is they're two expressions that only differ by one sign. Okay, they only differ by one sign. So if we look here to figure out the difference between the two polynomials, right, we can subtract the second from the first polynomial, trying to find the difference between them, right? We rearrange our terms. Ooh, keep sliding. We rearrange our terms, we simplify. So what this actually can do here is we can then rearrange it into something we're more familiar with, right? So our Pythagorean type theorem, right? So where we would have c squared is equal to a squared plus b squared. And if you look at it here, we are then left with something in the form of c squared equals a squared plus b squared. Again, where a is this value here, or sorry, c is this value here, a is this value here, and b is this value here, right? So then we can arrange it like the Pythagorean theorem. All right, and what this then does for us is we can even go further, and then the equation is just like in the Pythagorean theorem form. All right, so if we look here how this would apply to actual values, looking at the integers 5, n, and 3, okay, we could insert them in and result out with our answer. Okay, result out with our answer. So square the terms, simplify, okay, and what we're able to do is we're able to identify the triple. All right, so let me back it up here one. This is our c squared. All right, c squared is equal to a squared plus b squared. So we're able to figure out that our c value is 34, a value is 16, and our b value is 30. So that would be what's called our triple, identifying our triple value there. All right, now, noting here that it could also have those negative values, right? So if we were able to multiply that out, it could be those negative values, because negative values squared is still going to give you a positive value. So again, making sure that we're paying attention to our signs when we're doing our things here. All right, looking at another one here, we have this one called 2 squares, right? It's where you have 4 values and they're squared together. All right, and when we have the identity, it results in this AC minus BD squared plus AD plus BC, right? I think about it like foiling, right? A multiplied by C, A multiplied by D, B by C, and B by D, right? So looking at that there. But how we would solve this here, we would start off with our expression. We multiply the terms, right? Perfect. So multiply them out. Then we add and subtract 2a, b, c, d, right? That was that ending term. We rearrange our terms out, and then we simplify the squares. And that's, again, that's how we get out that final result there, right? Now, looking forward here, another one of those is our quadratic formula. All right, our quadratic formula. And we have a proof here, how to prove that x equals that using our quadratic formula. However, we're going to skip this for right now since we've done that quite a few times here. All right, so then just to confirm our polynomial identities, all right, those are expressions that are equivalent, right? So they're equivalent, and essentially they're like a shortcut, right? So if our expression matches, if our expression could match one of these identities, we can then kind of jump forward and not have to do all the complex values. We can jump forward and use this identity, which is an equivalent value of our expression. All right. So then moving forward here, again, this is where having that note sheet is going to be handy. But if you notice here, you've got your x squared minus 5. You've got your x squared minus your 5 value. All right, so how could it be written differently to express our difference of squares? So knowing what that's asking you here. Our Pythagorean theorem triple is generated by 5 and 1. Okay, so that would be, again, plugging that into our Pythagorean theorem, figuring out the calculations for our C, A, and B value, and then knowing which one is our triple. All right, again, expressing things in factored form, and then identifying which one is not a polynomial identity. Which one is not a polynomial identity. All right, so then looking here at our study guide. All right, looking at our study guide. Okay, again, the identity is an expression that is equal to, right? It's basically saying the same thing, but it's saying it in a different form that might be more usable for us. So, for example, here, our difference of squares, if we have a value that starts off like this or an expression, we could then change it into this new form in order for us to figure out, different characteristics about that polynomial. All right, same thing, difference of cubes. We have the sum of cubes, and we have our Pythagorean theorem triple generator, which is this equation here. We have the ability to look at 2 squares, and then our handy dandy quadratic formula there. Okay, and again, this one is really one that I suggest you look hands-on and do a couple practice problems with. It could be very, very helpful.